All right, good morning, everyone. Today we're going to talk about solubility, precipitation reactions, and net ionic equations. As far as solubility, we're going to be able to determine if a compound is soluble or not. We're going to be able to predict and write the equations for precipitation reactions, and we're going to be able to write molecular, complete ionic, and net ionic equations. So just remember that soluble means that it dissolves in a liquid, and insoluble means it does not dissolve in a liquid. As far as aqueous goes, aqueous specifically is talking about it dissolving in water. And again, for ionic compounds to dissolve, they will dissociate, which means break apart, into ions, which we'll get to in a little bit. So, compounds that break apart completely or completely dissociate, remember dissociate means breaks apart, those are going to be called strong electrolytes. And strong electrolytes, if we were to put a light bulb with electrodes in there, they would light a light bulb. As here. There must be ions in the solution to be a strong electrolyte. So they have to completely break apart. When polyatomics break apart, they do stay in their polyatomic form. So you will need to go in and check your polyatomic chart when we start breaking these. Because if it has a polyatomic, they stay as that one unit. But not all compounds will dissolve in water, so they're insoluble. If you notice here, this is a solid. So insoluble ones will make a solid in water, and they don't dissolve. They don't break apart. They just stay together in a solid form. Okay, here is a flow chart of if they're soluble or not. I need you to know these rules here. As far as your homework goes, you'll need to be able to use this chart on this specific slide to do the homework, although the paper homework has a chart of its own, but for mastering chemistry, you'll need to use this. As far as the test goes, though, you need to know the ones I put a little mark by. So all group 1 metals are soluble. So if it is in group 1, that first column, alkali metals, they're soluble. And then ammonium, nitrate, and acetate, those are always soluble. If those are present or a group 1 metal, it is soluble always. Okay, as far as the halogens go, they are soluble, except when there was silver, lead, or mercury. We consider those to be heavy metals, and so when a halogen is combined with one of those heavier metals, we say that it's not soluble or insoluble. Okay, everything else for the most part we just say is insoluble, unless it's got one of those things that I wrote down in red. All right, so we're going to go through, we're going to write our precipitation reactions. The biggest thing with this is that you remember your charges from your periodic table. You remember how to crisscross them. You remember ionic naming, things like that. Okay, so I've got sodium carbonate. Okay, and group 1 is soluble. Sodium's group 1. And then we've got copper chloride, and it does say copper 2 chloride, which is where that 2 came from. That is also soluble because halogens are soluble except with silver, lead, or mercury, which is not copper. Okay, when precipitations mix, we're going to talk about later, those are double displacement reactions. The metals switch places. So I'm now going to have copper with carbonate and sodium with chlorine. Okay, sodium is aqueous, so is chlorine because all group 1 metals are aqueous. I do not have a rule for copper or carbonate, which means it is solid because it is insoluble. Then we need to go back and balance. If I put a 2 here, that fixes everything. The reason I don't have any 2's on copper carbonate is because they both have a 2 charge, so they cancel. So it's going to walk us through all that. Okay, let's do one more for now. Potassium hydroxide. Potassium's group 1 metal, so it is soluble. And then we've got nickel 3 bromide, which is also soluble because that is not silver, lead, or mercury. We cross them. Again, metal switch spots. So I'm now going to have nickel with hydroxide. Don't forget it was nickel 3, so I need a charge there. And I've got potassium and bromine. Again, group 1 metals are soluble. We don't have any rules for hydroxide. We don't have any rules for nickel, so that's going to be our solid. Now we need a balance. I need 3 bromines, and I need 3 potassiums and hydroxides. So there we are. If you have questions on any of this, please reach out. Okay, as far as precipitation reactions go, which are what we were just doing, they will always form a solid product that we will call a precipitate. So that solid that is acting as a product is called a precipitate. So in order for a precipitation reaction to happen, we mix 2 aqueous solutions. They make that precipitate and then another aqueous solution, which we have seen. So here we've got our precipitate as our solid product. This is a precipitation reaction. Okay, if everything is aqueous on both sides, then we say that no reaction happened because everything is dissolved in solution. Okay, and again, it has to be a solid to be a precipitate. So in order to be a precipitate, they have to be insoluble, which means they're solid, they do not dissolve. Okay, so before we mix a solution, they're in separate beakers. They're broken apart because they're aqueous. Once we mix them in their containers, they're in one container now, but they're still broken apart. Once they actually start mixing, they form this lead 2 iodide precipitate. And now you can see it's a solid in the bottom of the container. Okay, remember our metals switch spots to make our new compounds of sodium chloride and copper carbonate. We've already done this one, but remember all group 1 metals are aqueous. We have no rules for copper or carbonate, therefore it's solid. Okay, we already did that one. And I'm just going to keep going through these. Oh, these are no reaction. Let's do one of these that's no reaction. So I've got ammonium chloride. Again, all ammoniums are aqueous. I've got iron 3 nitrate. All nitrates are aqueous. I mix them. My iron changes spots with ammonium because ammonium is acting as a cation, which is similar to a metal. So I'm going to have iron 3 chloride and ammonium nitrate. Now, ammonium nitrate is aqueous because both of those are always aqueous. We go to our iron 3 chloride. That is also aqueous because all halogens are aqueous except with silver, lead, and mercury. So, because everything is aqueous, we say this is no reaction. Now, it's not balanced. I need a 3 here, a 3 here. Now we're balanced, but still, it's no reaction. Okay, so there's more examples. If you need to go through more examples, please schedule tutoring. As far as the net ionic equations go, that's the next thing. Molecular equations are just normal equations. That's what we've been writing. Okay. Complete ionic, the aqueous ones break apart. So only break AQ into ions. Okay, so everything that ends with AQ breaks into its ions, but not solids, liquids, or gases, because only our aqueous ones break. So see, silver chloride stays the same, silver chloride stays the same. The ones that are the same on both sides are called spectator ions. Now, spectator ions are ones that don't participate in reactions. So a spectator just watches it happen. That's what we would call a spectator. Like if you went to a show and you were a spectator, you would be watching the show. You don't participate in the show, you're just there to watch. It's the same thing with these spectator ions. Again, in order to be a spectator ion, they need to be exactly the same on both sides of the reaction, as we can see here. After you get rid of the spectator ions, like you would do in math class, if you have the same, let's say if we have 3x on both sides of our reaction, or sorry, not our reaction, but our equation, you would just cancel them out because it'd be 3x and 3x, they go away. So it's the exact same thing with spectator ions. They're going to go away. And our net ionic is just whatever is left. So let's do we're going to do a complete ionic equation, and we're going to do a net ionic equation from this specific formula. Remember, that's called a molecular equation that they already gave us. So I've got Pb2+. That's because there's a 2 out here. That is lead charge. I have 2 nitrates. I have 2 of them because there's a 2 subscript. I have 2 lithiums. Lithium's charge comes from the periodic table. I've got 2 chloride ions. Again, charge comes from the periodic table. Now, lead chloride stays one solid piece because it's a solid. I can only break aqueous. And I've got 2 lithiums and 2 nitrates. If I were to start getting rid of things, my spectators, those ones that are the same on both sides, are my lithium and my nitrate. So my net ionic equation is Pb2+ plus 2 chloride ions yields PbCl2. So my net ionic is when I remove everything that's exactly the same on both sides. Okay, for this next one, the only piece that wouldn't break is a liquid because it's not aqueous. So everything else would break apart. We would cross out what's the same on both sides, and we get hydrogen plus hydroxide yields water. Okay, so this is just a summary. Molecular equations, normal equations we've been writing. Complete ionic, break everything that's aqueous. Net ionic, everything that's the same on both sides disappears. Okay. If y'all have any questions about precipitation reactions, how to tell if things are soluble, or net ionic equations, please reach out and let me know.